Alright, we'll get started with the Chapter 3 homework review. The overall performance on this was pretty good. We had an average score of 9.7 out of 12. It's a little bit lower than last time, but there are some pretty difficult concepts in Chapter 3, and they are going to be on the test this week, so hopefully we can clean some of these things up before long and be able to do okay on this with the exam. So most of the questions that I'll go over today were submitted by people in the class, requests from homework topics, and they mainly fell into a couple of major categories that as we'll see. And I also added a couple in that were questions that we didn't do as well on overall on the homework assignment. So we'll go over several of these, but like I said, they fall into just a few main themes, and hopefully once we sort of understand the concepts behind these, then any type of problem like this won't be too bad in the future. So a lot of the questions dealt with that people had dealt with percent ionic character or polarity. So the first thing we should get out of the way is that there are different ways of asking this question. So we could say more polar, which is the same as saying higher percent ionic character. So you'll see sort of both of these wordings. And so when you see ionic character, that just is another way of saying polarity. It doesn't really have any different meaning than that. And so again, then the idea is that when we have two atoms bonded to each other with the electronegativities being different, the bond is going to be polarized, which means that the electron density is going to reside more on one atom than the other. And so really the key concept here that drives all of these types of questions is what we abbreviate as delta En, the difference in electronegativity. And in general then, what you're going to see is that the higher difference in electronegativity correlates with the more polar bond, or as it is in this problem, the bond that has the highest percent ionic character. So if we're looking for highest percent ionic character, we're looking for the largest difference in electronegativity. And what we notice is that carbon is involved in all of these bonds. So really we're just comparing the electronegativity of one atom. So we have CO, CCl, CC, CH, and even though it's written NC, CN, doesn't matter what order you put them in. So we can eliminate a couple of these. If we're looking for the highest percent ionic character, that's going to be the most polar bond. If we have carbon bonded to itself, that's going to be completely nonpolar. So we can eliminate CC because this is going to be completely nonpolar. So anytime it's the same atom with itself, nonpolar bond, so we're not going to include this as the one that's being the most polar. But the rest of these are going to be polar, and we want to know which one is most polar. So for 3 of these bonds, the partner is more electronegative than carbon. So as we talked about in the exam review session, carbon is one of the least electronegative nonmetal atoms. And so if you have carbon bonded to any of the halogens except for iodine, it's going to be polarized towards the halogen. That's what we have in this CCl bond here. And then carbon, oxygen, carbon, nitrogen. So really of these 3 bonds that are polarized with delta plus on the carbon and delta minus on the other atom, the one that's going to be most polar is going to be the one that has the most electronegative atom that carbon's bonded to. Okay, because carbon is the lower electronegativity in all 3 of these cases. So if the other atom is more electronegative, you're going to have the bigger difference in electronegativity. So if you look at chlorine, nitrogen, and oxygen, their electronegativities go in that order. So chlorine is probably similar to oxygen. They have similar electronegativities. Sorry, chlorine and nitrogen have similar electronegativities, but oxygen is definitely going to be the most electronegative out of these 3. Because remember that oxygen is the second most electronegative atom on the periodic table behind fluorine. So this is going to be the most polar of those ones. But then we have to compare CO to CH. And CH is not a very obvious one because carbon and hydrogen are separated pretty far in the periodic table. But remember that hydrogen, even though it's in the same column as the alkali metals, it's actually a nonmetal, and its electronegativity is pretty similar to carbon. So in this case, you're going to have a slight partial negative on carbon and a slight partial positive on hydrogen. Carbon's a little bit more electronegative than hydrogen, but this one is essentially nonpolar. So anytime you see a CH bond, and this is going to be an important concept when you start taking organic chemistry if you go that far, anytime you see CH, that's roughly nonpolar. Alright, so it's not the most obvious one, but it is pretty much a nonpolar bond. There's only a very small difference in electronegativity, so that's going to leave carbon-oxygen as the most polar of these ones. So when you're comparing all covalent bonds, these are all non-metal atoms, it comes down to those trends in electronegativity that we learned from the periodic table, and in this case carbon-oxygen is going to be the most polar or have the highest percent ionic character. Let's do a few more like this. So we have pretty much the exact same question except worded in the opposite order. Which of the following bonds has the lowest percent ionic character? And this is again is another way of saying least polar. So here we're looking for the smallest difference in electronegativity. And really before, looking at all of these different choices, one thing we can say for sure is that if we have a metal with a nonmetal, those are going to be very polar or conventionally classified as ionic bonds. So if we're looking for the least percent ionic character, we can pretty much eliminate any choices that have metals with nonmetals, especially since two of our choices, A and C here, are nonmetal atoms bonded together. So we can eliminate choice B, D, and E because all of these are going to be ionic. Alright, and even though they're going to have different ionic characters, not all ionic bonds are exactly equal, if you have a metal with a nonmetal, those are always going to be very large differences in electronegativity, and they're going to be larger differences than you'll ever see when you have two nonmetals bonded together. So now we just have to really look at the two covalent bonds, CH versus HF. And again, we have a situation where they have the same atom in each of them, a hydrogen, and in both cases, hydrogen is going to be delta plus. So as we saw last time, CH is pretty much nonpolar, almost nonpolar. Slight partial positive charge on hydrogen, slight partial negative on carbon. And then HF, fluorine is the most electronegative atom on the periodic table, so this is going to have a very large partial negative charge on fluorine and a very large partial positive on hydrogen. This is going to have a greater difference in electronegativity. So again, C and H are very similar, but H and F are very different in terms of electronegativity because fluorine is way over on the right. So if you look at these on the periodic table, I should have done this for the last one too. Hydrogen again is up here, number 1, and it's a little bit out of place, but its electronegativity is very similar to carbon, so you can almost put it in the same region in the periodic table as carbon. So hydrogen and carbon are very close in terms of electronegativity, even though it's not obvious. And if you look at hydrogen versus fluorine, fluorine's way over here. It's the most electronegative atom, so there's going to be a bigger difference between hydrogen and fluorine than there is between carbon and hydrogen. And all the rest of these choices that were on this problem, which we've already eliminated, sodium, potassium, lithium with fluorine, chlorine, lithium, those are all metals here in the first column paired with nonmetals here in group 7. So whenever you have two atoms bonded together from such a far range of the periodic table, metal versus nonmetal, you're going to have a very polar or even ionic bond. Alright, so that's really the same concept, but this time we're looking for the least polar one, so we would select choice A. Alright, and here's almost an identical problem. Based on electronegativity trends in the periodic table, predict which of the following compounds will have the greatest percent ionic character. So we're looking for most polar or the greatest difference in electronegativity. And again, if we're looking for the most polar, we can quickly scan our answer choices. We see that choice A, HCl, this is two nonmetals, which means it's conventionally classified as covalent. And if we're comparing that to a bunch of compounds here that have metals with nonmetals, calcium is a metal, and these are nonmetals, strontium is a metal, fluorine and chlorine are nonmetals, we should automatically assume that the ionic bonds are going to be more polar. Now then we have to compare those four ionic bonds, but we can eliminate this answer choice pretty quickly because all the rest are ionic. And if we're looking for the most polar bond, we would expect it to be one of the ionic choices. Now for here we have to look at comparisons, and it might be helpful to do two at a time. So calcium iodide versus calcium chloride, we're looking for the more polar of the two. And again, this comes from difference in electronegativity, so it's calcium is going to be the least electronegative in both cases. It's the metal. The metal always has the positive charge on it, the partial positive charge. And we're bonding calcium to either iodine or chlorine. Electronegativity increases as we go up from iodine to chlorine. So chlorine is more electronegative than iodine, so this is going to give us a more polar bond. Alright, so we can eliminate that one, calcium iodide. And then if we compare calcium chloride to strontium chloride, so let's compare two that have one atom in common. That always makes it a little bit more straightforward. So calcium is here, strontium is below it, so strontium is less electronegative than calcium, so when we're pairing this with chlorine, which is more electronegative, the one with strontium is going to have the greater difference in electronegativity. So you're looking for the biggest distance in the periodic table going from bottom left to top right. Whichever is separated by a larger distance in sort of that basic direction is going to give you the largest difference in electronegativity. So calcium versus strontium. Strontium is less electronegative, so when it's paired with chlorine, it's going to have the more polar bonds. Alright, so this is going to be the more polar ones. We can eliminate calcium chloride. And now we just have strontium chloride versus strontium fluoride. And again, we have same metal, so whichever one has the more electronegative nonmetal is going to have the more ionic bond. And so chlorine versus fluorine. Fluorine, as I said, is the most electronegative atom on the periodic table. So when you pair that with a metal, that's going to always give you the most ionic bonds for any bond involving that metal. So strontium with chlorine versus fluorine is going to have a more polar bond when fluorine is the nonmetal, because fluorine is more electronegative. And so we can eliminate strontium chloride, and that leaves choice D as our most polar bond. So in this case, it's sometimes helpful to compare just two at a time and try to make comparisons where one of the atoms is the same, and then you're either just picking the least electronegative or the more electronegative atom that is partnered to find out what the most polar bond is. And then finally, a couple more like this. We're starting to beat a dead horse, but let's just go through all these so we can reason through all of them. Which is the most polar bond? We have IBr, KCl, SO, OCl, FF. Alright, so again, if we're looking for most polar bond here, we should automatically zoom in on ionic bonds. Alright, if any of our choices are ionic, we can automatically assume those are going to be more polar than any covalent bond, which is two nonmetals. So these are both nonmetals, but KCl, this is going to be an ionic bond, and the rest of these are all covalent. We can also eliminate this one because, as I said, if it's the same atom bonded to itself, it's completely nonpolar. So we have one ionic bond, we have A, C, and D are three polar covalent bonds. We would always expect the ionic bond to be the most polar. Alright, so the idea here is that, again, we don't have really two different types of bonds. There's not this sharp divide between covalent and ionic, but whenever you have a metal with a nonmetal, those are going to give you the largest differences in electronegativity, and so much so that you can almost classify the bond as ionic, which means that the metal has a full positive charge, the nonmetal has a full negative charge. So if you're looking for polar bonds, automatically search for ionic bonds first. Those are always going to be more polar than any covalent bond. And then this one here has a little bit of a caveat. So here we're looking for the most polar bond without being considered ionic. So in this case, if it's a metal with a nonmetal, we're going to automatically eliminate that because we're not looking for any ionic bonds here. Alright, and so if we look at these choices here, magnesium over here, number 12, Mg, is going to be a metal. So when that's bonded to oxygen, that's going to be considered an ionic bond. So this would be the most polar bond, but we're looking for the most polar covalent bond in this case, so we can eliminate choice A. We're looking for the most polar without being considered ionic. Now we have a bunch of other choices here involving oxygen. Carbon oxygen, oxygen, silicon oxygen, nitrogen oxygen. Again, oxygen bonding with itself, same atom with itself, is going to be completely nonpolar. So if we're looking for the most polar bond, that one's gone. But now we have CO, SiO, NO. So let's do carbon oxygen versus nitrogen oxygen. This is a pretty straightforward comparison. Because we look carbon here, carbon oxygen, nitrogen oxygen. The two that are closer together in the same row are going to give the least polar bond. So oxygen is more electronegative than carbon and nitrogen, but nitrogen's closer to it, so nitrogen oxygen is going to be less polar than carbon oxygen. So carbon oxygen is going to be more polar than nitrogen oxygen. And then if we compare carbon oxygen to silicon oxygen, there is some confusion here because silicon is technically considered a metalloid, and would this be considered an ionic bond or a covalent bond? Bonds involving metalloids are still considered covalent. We know that metalloids can have both metal and nonmetal character, but metalloids typically don't have full positive charges like you see in the metals. So their bonds, even though it's kind of arbitrary, I admit, these bonds are going to be considered polar covalent bonds, not ionic bonds. Alright, so these are both considered polar covalent, even though silicon is a metalloid. And so if we look at carbon oxygen versus silicon oxygen, again, oxygen is more electronegative than both of those, and so the biggest difference in electronegativity is going to come when we have silicon instead of carbon, because silicon is less electronegative than carbon, So the difference between silicon and oxygen is larger than the difference between carbon and oxygen. Or alternatively, they're farther apart in the periodic table when you go from bottom left to top right. Okay, so silicon oxygen is more polar than carbon oxygen, and that's going to be our winner in this case for most polar bond. Alright, so that's sort of the last one of those types of questions, and those are among the most difficult types that we'll see, because we're looking here at differences in electronegativity. You have to really think about the electronegativity trends for both atoms and try to rationalize which one is they're going to be the largest difference. And we try to make sure that all the choices are unambiguous. I mean, obviously, if you're comparing two things that are in vastly different parts of the periodic table, you might have difficulty, but we try to make the comparisons where there's going to be a clear winner in each case. Even if a couple of the choices are ambiguous with each other, there's going to be one that's no doubt the most or at least polar, depending on what you're looking for. Alright, and then this problem here is very similar, and we had some trouble with this one, even though I think it's a very straightforward question. So it's, which of the following has primarily ionic bonding? And remember that the big difference here is that a covalent bond is going to be two nonmetals, and then an ionic bond is going to be a metal with a nonmetal. So if we're looking for ionic bonding, we just need to find the pair that's a metal with a nonmetal. Just remember that metals are on the left side of the periodic table and nonmetals are on the right. You may also be wondering about what happens if it's two metals bonded together. That's called metallic bonding. That's something we won't talk about until much later in the course. So for now, we really only have two bond types to worry about, covalent, ionic, and they're just determined by the types of elements that are involved in them. So N2O3, CO2, CCl4, those are all covalent bonds because they're all nonmetals involved in those bonds. Alright, so we know that nitrogen and oxygen are both nonmetals. Carbon and chlorine are nonmetals. Carbon and oxygen are nonmetals. So all three of those answer choices involve exclusively nonmetals, so they're going to have covalent bonding. But if we look at rubidium oxide here, this is going to be our ionic bond because rubidium is over here. It's a metal. It's on the left side of the periodic table, group 1A, alkali metal specifically. And when it's bonded to oxygen, which is a nonmetal, that's going to be classified as an ionic bond. Again, the classification is somewhat arbitrary. There's really no fundamental difference between ionic and covalent bonding, but whenever it's a metal with a nonmetal, conventionally we classify it as being ionic. So that's going to be choice B for this one. Alright, so then we had a couple questions here dealing with bond energy or the strength of bond. So we're looking here for the strongest bond in the following group. So I think some people tend to overthink these questions and try to bring in ideas about polarity and things like that. There is some effect on bond strength depending on how polar the bond is, but it's not a very predictable effect. So when we ask you to find the strongest bond, here's really the only trend we want you to understand. The strongest bond is going to be the shortest bond, and vice versa. So you're looking for the weakest bond, it's going to be the longest bond. So if we're comparing two bonds, we just want to figure out which one has a shorter bond distance. The one that has the shorter bond distance is going to be smaller. The other thing also is that we have to remember that bond order sometimes plays a role in this. It's not going to matter in this question because these are all single bonds, but higher bond order is going to also correlate with the shorter or stronger bond. Alright, but really it's the same concept. You're looking for the shortest bond, which is going to be the strongest bond. If bond order is a factor, that also then, of course, relates to the strength of the bond as well. But here we have all single bonds, and all of them involve carbon. So if we're looking for the shortest bond, so we're looking for the strongest bond, we're looking for the shortest one, that's going to be the one that has the smallest atomic radii that are involved in that bond. Alright, because if you have two small atoms bonding to each other, those are going to give you a shorter bond than if you have two large atoms. All of these bonds have carbon in them, so really we're looking for, in which case is carbon bonded to the smaller atom. So it's going to be sulfur, oxygen, carbon, nitrogen, fluorine. And if you look at the trends in the periodic table for atomic radius, remember that the radius decreases as we go from left to right, and it decreases as we go from bottom to top. So sulfur is going to be the largest of those because in the the third row of the periodic table, so it's going to be larger than nitrogen, oxygen, carbon, and fluorine. And then if we look at carbon bonded to, again, itself, nitrogen, oxygen, fluorine, CC is going to be the longest bond because carbon is bigger than nitrogen, nitrogen smaller, so CN is going to be a smaller bond, and the smallest of these is going to be fluorine. So the carbon-fluorine bond is expected to be the shortest bond because fluorine is the smallest atom that carbon is bonded to in this problem. So that's going to be CF. Alright, so when we're looking at trends in bond strength, we're really thinking about the trends in bond length, which comes down to the atomic radii of the atoms that are bonded together. And if you want a shorter bond, you want smaller atoms bonded to each other. In this case, all the bonds have one atom in common, so we're just finding the atom that carbon is bonded to that's the smallest of these five, and that's going to be fluorine, which would give us the shortest bond. And then this question is sort of the opposite. We're looking for the weakest bond, and so again, that means the longest, which means we want the largest atomic radii for the two atoms that are bonded together. So we have PP, PF, PCl, PBr, PI. So phosphorus is in the same row as phosphorus chlorine. So phosphorus is going to be, let's do two comparisons at a time. This one's a little bit difficult. Alright, we're looking for the longest bond. So PP versus PF. Phosphorus is here, number 15. F is here, number 9. So phosphorus is larger than fluorine. Anytime you go down a row in the periodic table, you'd expect it to be larger, and it's also to the left. So phosphorus is larger than fluorine, so the phosphorus bond will be longer and weaker. So if we're comparing bond length, phosphorus is larger than phosphorus fluorine, so that's going to be our winner so far. We're looking for the longest bond for trying to find the weakest one. So then if we compare phosphorus to phosphorus chlorine, phosphorus and chlorine are in the same row, so as we go from phosphorus to phosphorus chlorine, chlorine here is smaller than phosphorus, so that's going to give us a smaller bond. So again, phosphorus is larger. If we compare that phosphorus bond to phosphorus bromine, though, phosphorus is here and bromine is here. Now this is a little bit of an ambiguous comparison because we're going down, which we expect the atomic radius to increase, but we're also going to the right, which we expect the atomic radius to decrease. Now one thing we should be aware of is that going down in the periodic table is a much larger impact on the radius than going left to right, especially when you have atoms that are clustered fairly close together like we are here in the nonmetals. Right, because when you go down the periodic table, you're adding a whole additional subshell. So the valence subshell for phosphorus is 3p. Now we're going down here to bromine is 4p, which is a lot farther away from the nucleus than the 3p. So bromine is expected to be larger than phosphorus, even though it is to the right. And so the phosphorus-bromine bond is going to be longer than phosphorus-phosphorus. But now if we compare phosphorus-bromine to phosphorus-iodine, iodine is below bromine on the periodic table, so iodine is larger than bromine, which means the phosphorus-iodine bond is going to be the larger of the two. Alright, so the longest bond unambiguously is phosphorus-iodide. This is going to be the longest, and then it's also then going to be the weakest because there's that inverse relationship between bond length and bond strength. Alright, so the correct choice here is E, phosphorus-iodine. Alright, the last three I want to go over deal with formal charge. And we had a little bit of trouble with these ones dealing with formal charge. So this one here, we're talking about the Lewis structure for sulfuric acid, and we're already telling you that it has 0 formal charges. We need to draw a structure that has 0 formal charge with sulfur as a central atom and no bonds between sulfur and hydrogen. So the first thing we need to think about, what's the formula for sulfuric acid? This comes down to nomenclature of acids. So sulfate is SO4 2 minus, and so we have to pair that with 2 hydrogens. So the correct formula for sulfuric acid is going to be H2SO4. Alright, so if you didn't have the formula for sulfuric acid correct, it's unlikely you drew the Lewis structure correctly. Now that we have the formula, let's follow the guidelines in the problem to draw the best Lewis structure. So we have, now we could also count valence electrons. Maybe that's a good idea before we start. So hydrogen has 1 valence electron each. And then sulfur and oxygen have 6 each. They're both in group 6. So we have 1 sulfur, we have 4 oxygens with 6 valence electrons. So we have 32 electrons if I counted those correctly. So So we want to make sure that the structure we draw only has 32 valence electrons, and well, exactly 32 valence electrons, and not go beyond that. So as the problem tells us, we're going to put sulfur at the center, and we have no bonds between S and H, so that means we need to have 2 bonds between OH. So both of our hydrogens need to be bonded to oxygen, and then the rest of the oxygens are going to be bonded to the central atom sulfur. And now we just have to start completing octets. So the oxygen, all the outer atoms should have complete octets. So we're going to add 2 lone pairs to each of these. Each of these oxygens at the moment has 2 bonds. They have 4 electrons, so we're going to add 4 more to complete the octet. And then these oxygens here only have 1 bond. Alright, so at this point we've used all 32 of our valence electrons, but if we count formal charges here, we see a problem. So the sulfur at the center right now, it has a complete octet, it has 8 electrons around it, so it doesn't need more. But we also are told in the problem that this structure should have 0 formal charges, and if we calculate formal charge at this point for sulfur, sulfur has 6 valence electrons, it has 4 bonds, and then it has no lone pairs. So right now sulfur has a +2 formal charge, and each of the oxygens has 6 valence electrons as neutral atom, 1 bond, and 1, 2, 3, 4, 5, 6 non-bonding electrons, -1. So right now we have a situation where we have -1 formal charge as an oxygen and a +2 on sulfur, and we're trying to find a Lewis structure that doesn't have any formal charges at all. So remember, the way we do this is if we have a negative next to a positive, we can take off one of the lone pairs, eventually, make it a double bond. We take off one of the lone pairs from here and make it a double bond. And now we've removed all our formal charges. So if we recalculate the formal charge for sulfur and oxygen with this structure, where we have 2 sulfur oxygen double bonds, our sulfur now still has 6 valence electrons as an atom, but now it has 1, 2, 3, 4, 5, 6 bonds, and it has 0 lone pairs still. So the formal charge in sulfur is now 0. And then if we look at oxygen, these oxygens have 6 valence electrons as an atom, 2 bonds, 4 non-bonding electrons, also 0 formal charge. Alright, so by drawing those 2 sulfur oxygen double bonds, we've gotten rid of the formal charges. This is going to be the best Lewis structure. So now we just have to count single and double bonds. We have 1, 2, 3, 4 single bonds, 2 sulfur oxygen, 2 OH bonds. So we have 4 singles, and then we have 2 double bonds between sulfur and oxygen to get rid of those formal charges as we showed. Alright, so 4 single, 2 double is the best answer for this one. Alright, and then here is another question dealing with formal charge. In this case we're looking for the formal charge on chlorine in the structure shown for the perchlorate ion resonance form with 2 ClO bonds and 2 Cl double bond O's. I don't think this one had a structure drawn for you, but we can draw this based on the information in the problem. So perchlorate is ClO4 minus, and so we have 1 chlorine that has 7 valence electrons. We have 4 oxygens that have 6 valence electrons each, and then we have 1 negative charge, which is going to give us an additional electron. So again, this structure here has 32 valence electrons. And we're drawing a resonance form that has 2 ClO single bonds and 2 ClO double bonds. So we can just start with exactly what it tells us to do, which is 2 single bonds and 2 double bonds, and now we complete the octets of the outer atoms. So each of the oxygens that's double bonded gets 4 more electrons, each of the oxygens that's single bonded gets 6 more electrons to complete the octet. And so this is going to be our structure here, where each oxygen has exactly 8 electrons. The outer atoms should almost always have exactly 8 electrons, and our central atom then has more than 8 electrons, which is okay because it's in the 3rd row. And we also should count electrons, so 4 oxygens with 8 electrons each is 32, so we don't add any lone pairs to the central atom. So this is the structure of perchlorate with 2 single bonds and 2 double bonds. And now we want to calculate the formal charge on chlorine for this structure. Alright, so when we counted valence electrons, we saw that chlorine is in group 7. It has 7 valence electrons. We subtract the number of bonds, so right now it has 1, 2, 3, 4, 5, 6 bonds. 2 singles and 2 doubles is a total of 6 bonds. And then we subtract the number of lone pair electrons on the central atom, number of non-bonding electrons, there are none, and so chlorine then is left with a +1 formal charge. And we can also verify that these two oxygens with single bonds are -1, so the sum of the formal charges does equal the overall charge, which is -1. But here we only needed the charge on chlorine, and so we calculated that to be +1. And then finally here, the formal charge on the nitrogen in the nitrite ion, NO2-. Alright, so this one we're going to have to draw from the beginning, so we weren't really given any information about its structure except for its formula. So nitrogen is in group 5 of the periodic table. It has 5 valence electrons. Oxygen is in group 6, so it has 6, as we've seen multiple times already. Two oxygens with 6 electrons each is another 12. And then we have our negative charge, so don't forget about that. We add one more electron to account for the negative charge, and we get 18 valence electrons in the structure. So we're not told about anything about the structure except for the formula, so we're going to draw the best one we can that completes the octets and minimizes the formal charges. So NO2-, we start with 2 nitrogen-oxygen single bonds. We complete the octets for oxygen. So we've now used 2 times 8, which is 16 of our 18 electrons. That means we have a lone pair. Now if we look at this structure, before we even start evaluating formal charges, we notice that nitrogen has an incomplete octet. It only has 2, 4, 6 electrons. 4 electrons in bonds, 2 as non-bonding electrons. So we automatically know that we need a double bond here. And so what we're going to do is we're going to take one of these lone pairs off of oxygen, it doesn't matter which one, and we're going to change that to a double bond to complete the octet of the central atom. But because nitrogen is in the second row of the periodic table, both nitrogen and oxygen are, we're not going to go and we can't expand the octet. So anytime you're dealing with these 2p elements here, carbon, nitrogen, oxygen, fluorine in particular, you're never going to expand the octet. And so we stop here. And now we just have to calculate the formal charge on nitrogen. So nitrogen has 5 valence electrons as an atom. We subtract the number of bonds, which is 1, 2, 3. 3 bonds, 1 single and 2 double. And then we subtract the number of non-bonding electrons. There are 2 non-bonding electrons, 1 pair on nitrogen. Those count individually, and so we get 0 formal charge on nitrogen for this structure. So the best Lewis structure for nitrite has no formal charge on nitrogen. The negative formal charge is on oxygen. And then there, of course, is going to be a resonance form for this, where we could move the double bond to the other side, but the formal charge would still be the same in this case. Alright, so there is resonance in this case, but all that changes is where the negative formal charge is located. It's always going to be on oxygen, never on nitrogen. Alright, so that takes us to the end of this review. Please contact me if you want any additional clarification on any of these problems or any other homework problems that I didn't go over. I hope, wish you the best for the exam this week, and again, please come by and see me if there's anything I can do to help you in your last-minute exam preparation.